Hello everyone. As in our previous lecture, we have to drive the relationship between the shear stress, shear force, section parameters with length and some area moment. So, what is the derivative part? We repeat in this lecture. We drive that Q will be equal to shear stress will be equal to shear force upon my B is the width of the section I into A into Y bar. This is both most important derivative part. So on the basis of this particular formula, we have now calculate the distribution of particular shear stress on the different sections. So now we take first example of rectangular section. So here we see in the rectangular section we consider the b is the width of the some rectangular section, d is the depth. So from the neutral axis this is divided into d by 2 d by 2. We consider one section, shaded section, and the distance from this shaded section to the neutral axis is y, and from this CG to this neutral axis is our y bar. Okay, so this is the derivative part, that means the distribution of shear stress. We have to write the distribution part through the formula which drive in our previous class. So let's start. We know that this shear stress formula, and we just put the value of area y bar in this particular expression. So what is the value of area? Area will be equal to v into d by 2 minus y. How? Area for this section, how was the area of this section? So b is this width, and the we want to calculate this thickness, so thickness will be equal to d by 2, this d by 2 minus y, this is thickness. So this into this is become a rectangular. So this is the rectangular area which is put here, b into d by 2 minus y. And what is the value of y bar? As I told earlier, y is the value of this two, from this CG to this neutral axis. So this is become y plus dy 2 minus y plus dy 2 minus y dy 2 minus y by 2. This is the value of y bar. So now we check y plus half of dy 2 minus y, correct? So we know the value of a into y bar. We just put in this value in this equation. So a into y bar will be equal to this b by 2 d by 2 minus y multiplied by half d by 2 plus y. After the cancelling this two terminology, we drive this equation b by 2 multiplied by d square by 4 minus y square. So what the remaining terms in this formula? Here we calculate this a into y bar. This is the moment of inertia. So moment of inertia for the rectangular section is bd cube by 12. So we put all these things a into y bar and I on this equation. So what we found? We found this equation. Okay, so from this equation you find out the distribution. Formulate this equation 6f bd cube d square by 4 minus y square. So you just see from this equation this value of this shear stress will be become mostly depend upon the value of y. Y is the value of neutral axis to the particular section. So y, when the y value is maximum, that means y is equal to d by 2. So which we put when y is equal to 0, the q will be equal to 0. Suppose this is d by 2, this is d by 2. So when we put y is equal to become d by 2, so our shear stress will be value is equal to 0. And similarly we put y is equal to negative d by 2, so also the shear stress value will be become 0. So where is the maximum value come? So when we put y is equal to 0, that means the y is equal to 0, that means the neutral axis. So the value of shear stress will be equal to 6f bd cube into d square by force, which will be equal to 1.5 times of the f into bd. Q maximum will be equal to 1.5 multiplied by f into bd. So here is some value we got on when drawing contouring these particular values. So 8 d by 2, here 0, here 0, so this form become a parabolic shape. So from this derivation we found that the shear stress distribution on the rectangular section is parabolic, and the maximum value of the shear stress is become 1.5 times of the fbd. And the value, what is the value of this fbd? F upon my bd. So F upon my bd is just our shear stress. So because the shear stress is the force upon my area, so area is become a into d, and f is the force, so which was denoted by q average. So the most important things which will be observed from this derivation is the maximum shear stress will be equal to 1.5 times of the b f upon my bd, and which is equal to which is noted as 1.5 times of the q average. That means the average shear stress, maximum shear stress is a 1.5 times of the average shear stress. So these two things is very important, and it is asked in the various competition exams like gate. So this types of question is asked that in the rectangular section, what is the maximum values, how much time of the maximum value to the average value, like 3 by 2, like 4 by 3, like 1 by 2. So the correct answer is 3 by 2, that means 1.5 times of the q average. So it is summarized here, the rectangular section maximum shear stress is the neutral. One more thing, the maximum stress comes at the neutral axis, okay, not the top and bottom of the particular section. This occurs on the neutral axis. And when we see in the bending stress distribution, the bending stress distribution is like in the center the bending stress becomes 0, and here is the minimum. Just opposite the distribution of shear stress, here is the 0 and here is the maximum. Okay, we know that this theory, because here is the shear force is maximum and here is the bending stress is 0. Okay, so here one derivation is completed. So I give one assignment to you. You try the circular section. Similar, I give some hint to you, like this is one circular section. You consider one element, okay, the thickness of this element you consider dz, and the which is y z distance to the neutral axis, and the various angle you consider theta phi from the radius to one end to another end. This is the b, this is d. So you calculate the width, then z from the circle properties. This is very easy to calculate. Then dz, this all things is calculate easily. Then area of this rectangular we consider dz into b, moment of, then moment of area a into y or a into z. So you put all this value and then integrate this to theta to 5 by 2, because this value is theta, 5 by 2 means 180 degree. So you just derivate, integrate this value to 180, put all this value. So you got the value of a into y bar throughout the cross section, and value of I. You just put same thing, try to shortening the derivative part. Here you put 1 minus sine square theta is equivalent to put the value of sine theta y by d by 2. Here is theta, so sine theta will be equal to y by d by 2. D by 2 is the value of this is d by 2. You put all this value and drive, and also is similar, you put the value of y. So when value of y will be equal to 0, q will be equal to 0, and y is equal to d by 2, q is equal to 0, and y is equal to 0. You get the value of 16 by 3 f by d square. So you convert this to 4 by 3 f by 5 pi by 4 d square. So here the pi by 4 d square is the area. So f by area is the average stress. So now you found that in case of circular section, the value of shear stress will be equal to 4 by 3. Maximum shear stress value will be equal to 4 by 3 times to the average shear stress value. So in case of rectangular, this value is become 1.5 times of the q average. In case of circular section, this value is become 4 by 3 times of the q maximum. So you just try to drive this derivation. If anyone have doubt, then ask me at any step, because your syllabus is very large, so I want to skip this portion of your syllabus as soon as possible. So you do some exercise in your home. And last one is the isoscale triangular section. So same thing you do here. Here is your isoscale triangular b, and height is a h. So you know that the CG of this triangle will be equal to h by 3 and 2h by 3. So you consider one small element here. So from this CG to this CG, this is your y, this is your neutral axis. So from top and from bottom, different axes. So just try the area of this AA will be equal to half into b dash by y. Area above this AA, what is the AA section? this is AA. So this is how much the area, half into B into height is the consider as Y. So Y will be equal to H square by, from this isoscale principle you calculate this value of Y. So Y will be equal to, the come is equal to, B dash will be equal to A B into HY. From this principle you calculate this value of B dash. So B dash by B will be equal to Y by H. So B dash will be equal to Y into B by H. So you put this value here. You got the centroid from the top 2 by 3. Centroid of the top CG is 2y by 3. You know the distance of the shaded area of the AA from the neutral axis. You know the CG. So 2h by 3 minus 2y by 3 is the CG y bar. This is 2h by 3 and 2y by 3. So this is the y value, you know, and you put then again a into y bar, and the moment of area will be equal to bh cube by 36. Then you put all this value here. So on compressing you got, on shortening this derivative you got this value. When you put y is equal to 0, then this all the terms become 0. Y is equal to h, all terms become 0. So here you know, at y is equal to 0, that means at y is equal to 0 you consider y from the top. So in this case you consider y from top. So y equal to 0 and y is equal to s, both the value of shear stress distribution is will be equal to 0. And at the centroid of the circle, that means the 2h by 3, the value is become 4 by 3 f bh by 2. Bh by 2 is the area, b into h into half into b into h is the area of the triangle. So this is become 4 by 3 q average. And one more thing, this is the we have to find out the maximum shear stress. So for maximize this thing, maximize anything, we know that the for maximization we just del q by del y will be become equal to 0. So we derivate these terms first time and put this value is equal to 0 to know the maximum value. So here you got y is equal to s by 2. So from this, because this is the triangle section, not uniform, non-uniform section, so here chance of the getting maximum shear stress value, because at 0 and h you know the value of 0, but h 2h by 3 you determine this value. So here is one chance to get one maximum value. So that's why we put this value to, this is 2h by 3 and this is h by 2. This value is derived from this maximizations application. So put this value of y is equal to h by 2. You found this summaries. That means q maximum will be equal to 1.5 times of the q average. So now this triangular section you found two things. First things, the maximum value of the shear stress will be equal to 1.5 times of the q average, and at their CG the q the value of shear stress, that means the 2h by 3, this value of shear stress will be become equal to 4 by 3. times of the neutral axis. So on the isosceles triangular section, the shear stress on the top and bottom extreme will be equal to 0, and the maximum value is 1.5 at the mid depth, and has a become value will be equal to 4 by 3 q at the neutral axis. Neutral axis found the value 4 by 3, and in the mid we found the value of shear stress is 1.5 times into q average. You check the figure of this shear stress distribution. Okay, yeah, this three derivation is very important. You once practice this three derivation at once. In most of the exam, the derivation is asked as, or otherwise this derivation, these relations between the shear stress and the average shear stress and maximum shear stress and the location is also found in the, also asked in the exam. So you must know the these things in depending upon this section, like rectangular, triangular and circular section. Okay, I have to stop here. In the next class we will do some practice of some questions. Okay, thanks.